Okay, welcome back to chapter 13. We're going to cover all the remaining trig identities in this video and practice them a little bit. Just as a recap, going back to our formula book for topic 3, circular functions in trigonometry. This first box, we saw this back in chapter 10, arc length, sector area. Second box, we've seen this already, I think back in chapter 12. We've got some reciprocal functions here. We've got tangent. They don't even define cotangent on here. That's ridiculous. I've never actually had this thought until this exact moment. Wow. Anyway, we define tangent in terms of sine and cosine. Secant and cosecant, they tell you what that is, and you need to know what cotangent is, I suppose. And then we have three Pythagorean identities, so-called because we have something squared plus something squared, and the first one is coming from the unit circle and making right triangles there. This video, we're going to cover all of this stuff. They're really good. We're going to use these a lot. And the final formulas, we saw these back in chapter 11. So that's going to be it for the formula book for topic 3 pretty soon. Okay, let's jump in. So here again, we've seen these identities before. Let's just use them real quick to expand and simplify. What are we looking at here? We're looking at a binomial that we need to square. So this is a minus b squared. We know how to do that, right? We're just going to, it's going to be a squared minus 2ab plus b squared. That's what we got here. But then we notice, hey, look at this. I got a cosine squared plus a sine squared. The book rearranges it in this step, whatever. The point is, those two together make one. Okay, simplest form. So we just got to, stuff like this needs to be comfortable and easy for us. Let's look at a couple of other ones. Just simplifying these. Okay, I think this first one, well, what could we do here? Can we factor anything? Let's see. Yes, indeed we can. We can take out a 2, and then all of a sudden, that's a difference of squares right there. So that's going to be 1 plus cosine and 1 minus cosine, which means that we can cancel out the 1 plus cosine with the denominator, and then that's our final answer. And over here on the right, can we factor anything here? Yeah, same idea, right? The denominator is now a difference of squares, so we should be able to factor that and then cancel with the numerator. Okay, no big deal. Point is just, don't panic if you see some weird looking expression with a whole bunch of trig stuff. Just do some basic algebra. You're going to be fine. Okay, so now we've got new identities. These are called the double angle formulas. So they turn up quite often, needing to know what sine of 2 theta is, cosine of 2 theta, or tangent of 2 theta. Defining them each in terms of sine, cosine, or tangent of 1 theta. Now, sine of 2 theta, very straightforward. Tangent of 2 theta, very straightforward. Cosine of 2 theta is the interesting one. There are 3 different formulas for it, and they're all equivalent. You could use any of these 3 anytime that you run into cosine of 2 theta. It just so happens that most of the time, one of them is going to be the easy mode, and the others are going to be either more challenging or just impossible. So that's the only trick here is just kind of thinking ahead a little bit and choosing the correct form of cosine of 2 theta for what you need to do. And sometimes it won't matter, but sometimes it really will. Okay, so let's jump into some easy stuff down here. So here we know what sine of alpha is, and we know what cosine of alpha is. I want to take a moment to point out that we are definitely in the second quadrant here if sine is positive and cosine is negative. That may or may not be relevant. I don't know. Let's figure out what sine of 2 alpha is then. Okay, so sine of 2 alpha, using the formula above, that's just going to be equal to 2 times sine of alpha times cosine of alpha. So we just substitute those in. There we go. We got ourselves an answer. Cosine of 2 alpha. All right. In this case, it's not really going to matter which one of them that we use. They've used the first one. They know what cosine is. They know what sine is. So they square them and subtract. I assure you, if you'd used any of the other 2 formulas in this case, it would have been just fine. Is it surprising here that sine of 2 alpha became a negative number if we were in the second quadrant? Well, hopefully not, because if we take any angle that's in the second quadrant and we double it, right, we're going to end up somewhere. It's not obvious exactly where, but somewhere down there. Right? Something that's just bigger than 90 degrees. When we double that, it's going to be a little bit bigger than 180 degrees. Something that's just a little bit less than 180 degrees, when we double that, it's going to be a little bit less than 360 degrees. And in both of those quadrants, sine is negative. Now, cosine is only positive in one of those two. So this will kind of help us figure out where in quadrant 1 our original angle was, in quadrant 2 our original angle was. Since we ended up getting a positive value out here, that means that 2 alpha is actually going to be in quadrant 4, which means that 1 alpha was originally somewhere in the second half there of quadrant 2, which, you know, if we had really thought about how this would have looked given the values that we had, we know that where would our point have to be for us to have a sine of 3/5? Remember, the sine is going to be the opposite over hypotenuse, which means that our y values needs to be kind of smaller than our x value was. Had we maybe switched these, if this had been 4/5 and negative 3/5, then our triangle would have looked more like that, and then we would have ended up with a negative value down there. Anyway, I'm overanalyzing this. I'm just trying to help you see what's happening, but none of this last couple of seconds is actually crucial in any way. All right. Next step. Okay, so now we're actually being told in this case exactly what quadrant alpha is in. So now it is important for us to know this. In the previous one, we knew what cosine was. They told us in advance. In this one, they haven't told us what it is. Doesn't mean we're not going to need to work it out. So we know what sine of alpha is. It's 5/13. Let's find the exact value of sine of 2 alpha. We know that sine of 2 alpha is going to be 2 times sine of alpha times cosine of alpha. So we're going to need to figure out what cosine of alpha is. The way that the book does it is by using the Pythagorean identity, cosine squared plus sine squared is equal to 1. Okay, we know what sine is, so we square it. And then we find out that cosine has to be one of these two values. It's got to be either plus or minus 12/13. But we're told that alpha is in the second quadrant, which means that cosine has to be negative. So we can work out then that cosine of alpha is equal to negative 12/13. Okay, cool. The other way that you could think about this, especially since this one is such a well-behaving triangle, is, you know, if we know, just to draw an arbitrary triangle here, if this is alpha, we're told that its sine is 5/13. Okay, so what does that make the third side of this triangle? That's pretty obviously a 5, 12, 13 right triangle. So that tells you, again, that cosine has to be either plus or minus 12/13, and then you can work out what the third, whether it's positive or negative in the same way as we did before. So you're either using cosine squared plus sine squared is 1, or you're thinking about right triangles to figure out what that third side is, whatever makes you happiest. Okay, anyway, now I think the rest of this should be pretty straightforward, right? We substitute in sine and cosine here, and we get a value for sine of 2 alpha. As far as tangent is concerned, tangent of 2 alpha requires us to know what tangent of 1 alpha is first, so we'd work that out. Having calculated sine and cosine already, we can easily deduce what tangent is, and then we can just substitute that into its formula, do a little bit of simplification, and there we go. Similar thing here. Now we're just kind of working backwards. Now we know cosine of 2 alpha is 3/4. We want to figure out what is cosine of 1 alpha and sine of 1 alpha. Okie dokie. I don't want to do that. Here we go. So if I want to figure out cosine of alpha, the easiest, remember that we said before there were 3 different identities for cosine of 2 alpha. Well, let's take a look at them real quick. 2 of them use sine in them. 1 of them does not. So for this particular first problem, we're going to use the version that doesn't have a sine in it, only has cosine. Okay, and again, that gets us to here. We've got a plus or minus again. So now, how do we know whether it's plus or minus that? Well, we're told that alpha is acute, and if alpha is acute, then we're either going to be in the first or the fourth quadrant. So either way, our cosine value is going to be positive. Okay, now for the second one, we've actually got quite a few options, right? So first of all, we could use this one here. We know cosine of 2 alpha. We could set that equal to 1 minus 2 sine squared and kind of work it out similarly to how we just did the previous one. We could also use this one here because we know what cosine of alpha is now, so we can just square that and then work out what sine squared is, and then take the square root and so on. But we can also go about this another way. Kind of an easier, more direct way is to use the Pythagorean identity again, right? Sine squared plus cosine squared is equal to 1. So rearranging, we can get sine is equal to the square root of 1 minus cosine squared. And then again, we know what cosine is, so we just square it, blah, blah, blah. And here we have it again. Now, we can infer from this, I mentioned before when I was talking about the answer to this first one, I said since the alpha is acute, that means we're either in quadrant 1 or quadrant 4. I was imagining an acute angle here or an acute negative angle there. Given that they have decided here that sine has to be a positive value, that means that we're strictly dealing with quadrant 1. So the book must not mean negative angles when they say that that the angle is acute. I don't think that that's an agreed upon definition. I think that's kind of a gray area in mathematics. I would certainly refer to that as an acute negative angle, but I don't know. Maybe I'm wrong. Maybe the word acute means it has to be positive. Anyways, don't worry too much about that. On an IB exam, it'll be pretty specific. It'll be very specific what the domain should be. Okay, so now that brings us to the compound angle formulas. Okay, so this is when we have cosine or sine or tangent of two angles that are being added or subtracted together. Now notice that like these simplify to the double angle formulas if you make A and B the same thing. Right? So if we were to do sine of A plus A, clearly that's equal to the sine of 2A, right? And we know that that's equal to 2 sine A cosine A, and that's exactly what we would get out of this, right? Because we'd have sine A cosine A plus cosine A sine A, so it's clear it's going to be 2 sine A cosine A. But these are the more general formulas when the two angles are not the same. Again, in the formula book, so you don't need to memorize them. Pay close attention over to the plus or minuses. So these are always plus or minus, but you'll notice right here we have a minus plus. What that means is if it was a plus here, then it's a minus here, and vice versa. Okay, so the compound angle formula for cosine is going to switch signs when we get here. Whatever was inside is going to be switched. Sine is going to be the same. Tangent, the numerator is the same, but the denominator gets switched. So just be mindful of those. Don't go through this too fast and miss that, because that's you'll be very sad with yourself if that happens. Anyway, simplifying. Okay, so we've got cosine of 3 theta times cosine of 1 theta minus sine of 3 theta times sine of 1 theta. This is impossible if you don't know your compound angle identities, right? So look at this. It's the right-hand side of this one. So in this case, A is 3 theta and B is equal to 1 theta. So working it backwards, since that's a minus right there, that means that it originally had to be a plus. So this is going to be the cosine of 3 theta plus 1 theta, which is cosine of 4 theta. So now these compound angle formulas enable us to now work out exact sine, cosine, tangent functions for various other angles, not just multiples of 30 degrees and 45 degrees, but we can work at other ones, like for example here we have 75 degrees. How can we do that? Well, 75 is just 30 plus 45, right? So that's all we need to know. Then we use the compound angle formula. We know what sine of 45 degrees is. We know what cosine of 45 degrees is. Same for 30. We substitute them in and simplify, and there you go. Got that. All right. So it's been a couple of times in the past when the IB's asked something like this on an HL exam. Sometimes it'll be, could be like 75 degrees, could be like 15 degrees, could be 175 degrees. Often it's in radians, whatever. You got this though, right? Okay. So now, this is one of my favorite ones. All right, I'm going to make a big deal about this. The book doesn't make a big deal about it. I'm going to. You remember there was the first problem back in section A had an equation with a sine and a cosine together. Well, in this example, we're going to show how to combine a sine and a cosine into a single function, which in this case is going to be a cosine function. Okay, it's pretty cool, and it requires us to use the compound angle formulas. All right. I don't recall seeing this on a previous IB exam, but it's been in a bunch of textbooks that I've read, so I think it's a really neat technique, and I don't know, I think the IB should use it more often. So let's see, what can we do here? So we're supposing that sine of x minus root 3 cosine of x can be rewritten in this form here, but that's cosine of something plus something, so we can use the compound angle identity for cosine, and we can rewrite, and then we can even distribute the k. Okay, so now we have sine of x is equal to all this mess, and I just want to point out we've got a sine x here, we've got a sine x here, we've got a cosine x here, and we've got a cosine x here, and I want us to think back now to work we've done previously in this course, back when we had when we were looking at polynomials and their coefficients, right? And we would say the two polynomials were the same if the coefficients of each like degree term of x were the same. We're going to use the same idea here. If these two are equal, then one sine of x needs to be equal to negative k sine b sine of x. And root 3 cosine of x needs to be equal to k cosine of b cosine of x. Right, so we're equating the coefficients of cosine of x and sine of x. And then we're just going to, then have a system of equations, excuse me, right? So we've got k squared cosine b squared equals 3. And we've got k squared sine squared b equals 1. So in this case, they squared both of the equations. I don't think we needed to do it this way. We'll look at another method in just a moment. And then adding the two of them together, which sounds like a weird thing to do because usually we don't add equations together unless we eliminate something. But in this case, we're not eliminating anything yet. But we notice that we'll have k squared plus cosine b plus k squared times sine squared b. Factoring out the k squared, we've got cosine squared plus sine squared in there. That just becomes a 1. So we actually are eliminating the cosine squared and the sine squared. And then we just figure out, okay, k squared is 4, so k is either plus or minus 2. But we're told that k is positive, so k has to be equal to 2. And then from there, once we know what k is, then we can easily work out what cosine of b and what sine of b are. And then there's only one possible value for b based on those. Since they're both negative, then b must be in the third quadrant. And there we go. So this problem is really, there it is. It's about using the compound angle formula and then solving a system of equations. Now I said I probably wouldn't have done this like squaring of both sides. If it were me, I probably would have done something like solving for k. I think that would have worked out just fine. So we could say that k is equal to negative root 3 over cosine of b, but that has to be equal to, from this other side, negative 1 over sine of b. And then I would solve that right-hand side of the equation. I would rewrite this to get sine of b over cosine of b is equal to 1 over root 3. That's just tangent of b is equal to 1 over root 3. That Of course, now solving that, that's going to get us two possible answers, one in the third quadrant and one in the first quadrant. So the way we determine which of those was correct is if we had a value in the first quadrant, then both sine and cosine would be positive. But since we're told that k is a positive, then there's no way that a negative times a positive times a positive could be a positive. And likewise, over here, there's no way that a positive times a positive could be a negative. So that would inform us to know that we were in the third quadrant for sure. All right, so there's two different ways that we could solve that system. I really like this technique. I like problems like this. The first time I saw it, I was like, wow, you can actually combine a sine and a cosine and work out exactly what the new equation was. And I didn't think that was going to be possible. I just thought you got some weird random wave and that it was going to be very difficult to work out. But it's actually very doable. All right. And one of the things I really love about trigonometry is it's such a complicated, multifaceted topic of mathematics. Like it's got waves we were just talking about. It's got circles, and then but like what's trigonometry really about? It's really about triangles, right? I mean, that's literally the name of it. So let's do a problem with triangles, huh? So this is from the homework from this section, 'cause I think this is a cool problem. So prove that alpha plus beta has to be equal to pi over 4. All right, we don't have a lot to go on in the picture, but we do have a bunch of pieces that are congruent, so we can work out that sine of alpha is 1/3 and sine of beta is 1/2. And we want to say something about alpha plus beta. Well, the only thing that I could think of doing here is not actually answering what alpha plus beta is, but let's think about what the tangent of alpha plus beta is. Right? Because since we know what alpha and beta are, we can use our compound angle formula for tangent to figure out what this is, right? So tangent of alpha plus beta is going to be tangent of alpha plus tangent of beta, all divided by 1 minus tangent of alpha tangent of beta. And then we can simplify that, right? So we've got in the numerator, we have 1/3 plus 1/2. So that's 2/6 and 3/6. That's going to be 5/6. And then on the denominator, we've got 1 minus 1/6, which is actually, hey, 1 minus 1/6 is just 5/6, and that's equal to 1. So it turns out the tangent of alpha plus beta is equal to 1. What does that mean alpha plus beta must be equal to? Well, there's only one angle there's only one acute positive angle that has a tangent of 1, and that's pi over 4. So there we go. Let's do another problem from the book. They've actually got quite a few at the end of section E that I really enjoyed. So here, look, we talked about cosine of 2 alpha. We have double angle formulas, right? But we can also work out like triple angles and quadruple angles and such. I really like this problem in particular because this connects really well to chapter 16. When we eventually hit chapter 16, we're going to have a completely different method for coming up with this expression that actually uses complex numbers, and it's really cool. So I don't know, perhaps you'll remember this experience when we get up to chapter 16, and you'll be able to, I don't know, decide for yourself which method you prefer, but unfortunately it's going to be a while before we get there. So anyway, by replacing, obviously 3 theta is equal to 2 theta plus 1 theta, right? So that means that we can use our compound angle formula. This is going to be cosine of 2 theta plus 1 theta. And then we're going to, okay, so cosine of alpha plus, of a plus b, I should say. This is going to be equal to the cosine of 2 theta times the cosine of 1 theta minus the sine of 2 theta times the sine of 1 theta. Okay, I know that this piece over here on the right is going to be sine of 2 theta is equal to 2 sine theta cosine theta. I'm going to call that 2 sine squared theta cosine theta. Now, cosine of 2 theta on the left, remember that there are 3 different formulas for that. So it's not obvious just from looking at this problem which of those identities to use. All I can say is just try one, and if it becomes too much of a mess and doesn't really work out for you, then try another one. So in this case, we're going to go with the 2 cosine squared theta minus 1 all times cosine theta. We're then going to distribute through, giving us 2 cosine cubed theta minus cosine of theta. And then we're going to do something else that's not at all obvious, which is we're going to rewrite sine squared as 1 minus cosine squared theta. And the only reason I'm doing this is because if I try anything else, it's just going to lead to a dead end. So if at any point you're thinking, man, I wouldn't have tried that, I would have tried this other thing, pause the video, give that a go, and you'll probably end up at a dead end. Maybe some of them you can eventually work your way back, and it'll work out. I'll be honest with you, like I sat down and tried to do this one on my own, and it took me 3 or 4 attempts to get to it the right way. So spoiler alert, this method from chapter 16 is like way better than dealing with trig identities, but for now it's all we got. Anyway, from here now we're going to distribute this cosine through, so now we've got 2 cosine cubed theta minus cosine theta. Let's distribute the 2 as well, so then it's going to be minus 2 cosine theta, and then it's going to be plus 2 cosine cubed theta. Yes, we're there, right? Because we just combine these two are going to give us 4 cosine cubed, and then these two are going to give us minus 3 cosine. So, whew, there you go. That's how to do that. And then, oh, we didn't even answer the good part of the question. Hence, solve this equation. Well, let's do that, shall we? So, we've just shown that this identity is true. And we're now going to use that identity to solve this equation, right? Hence, so even if this were an exam, even if you had no idea how to do that first part, you can still do the second part because we're going to use that information. And right away, notice that if we multiply both sides of this by 2, then on the right we get 8 cosine cubed minus 3 cosine, and on the left we're just going to get 2 cosine of 3 theta plus 1. That should be equal to 0. Looking at this, by the way, we know that theta is in between negative pi and pi, which means that 3 theta is in between negative 3 pi and 3 pi. Okay, so since we know that the cosine value is going to be negative, that tells us that we need to be in quadrants 2 or 3. This is for 3 theta only. Okay, so let's figure out what 3 theta is going to be. So if it's going to be negative 1/2, okay, let's work our way around the unit circle in a positive direction right now. So in quadrant 2, the value for 3 theta, that's going to have a cosine value of negative 1/2, is going to be 2 pi over 3. Then we go into quadrant 3, excuse me, and then we're going to have 4 pi over 3. And then we're going to keep going. Cosine's positive here. We're going to keep going around again because we've got up until 3 pi here. So back in quadrant 2 for the second go round, we're going to have 8 pi over 3. Okay, now we've got to do the same thing. We got to go back in the opposite direction though. So when to get into quadrant 3 going this way, that means that we've gone, it's just going to be negative 2 pi over 3. Then we're back in the quadrant 2. That's going to be negative 4 pi over 3. And then we're back in quadrant 3. On the second go-round, it's going to be negative 8 pi over 3. So then we divide by 3 here, and we get theta is equal to, I'm just going to say plus or minus, it's 2 pi over 9, 4 pi over 9, plus or minus, and plus or minus 8 pi over 9. And those are the correct 6 solutions to this equation. Now, some of you may be protesting at this moment, hey, wait a second. This is a cubic equation. There should be at most 3 solutions to it, but that's true if it's a cubic polynomial. This is no longer a polynomial because it's 8 cosine cubed. Had this equation been 8x cubed minus 6x plus 1 equals 0, certainly there'd be at most 3 solutions to that, but again, that's polynomial. This is not polynomial because we've got trig. Let's do some more. Okay, so now we're gonna, I do recall seeing a problem or two that was similar to this on previous exams, so let's pay attention to this one. So we're using this identity, which, that this is one that's in the formula book that they're telling us, hey, use this one to show that arctan of 5 minus arctan of 2/3 is equal to pi over 4. And I mean, at first glance, it's like, how am I supposed to use that? On like this, there's no arctan in here. We just have tangents. So what can we do here?
So I'm sitting at home editing this video, and it turns out I just never pressed record for the next part, and I'm too lazy to go back to the classroom and reshoot it. So basically what I was going to say was, what does the arctangent function do? Well, it gives us the angle out if we know what its tangent was. So for example, arctan of 5, that's an angle. Let's call that angle theta. An arctan of 2/3, that's another angle. Let's call that angle phi. So the left-hand side of our equation is now rewritten as theta minus phi. And what we're going to do is just take the tangent of that and then use the compound angle formula for tangent. And then we'll see what happens from there.
So we can sub that in here. We've got 5 minus 2/3 divided by 1 plus 5 times 2/3. Simplify everything here. That's on top, that's 15/3 minus 2/3, which is 13/3. On the bottom, we got 3/3 plus 10/3. Hey, that's also 13/3. Well, surprise, surprise, it's all equal to 1. So we've just worked out that the tangent of theta minus phi is equal to 1. Therefore, arctan both sides, theta minus phi must be equal to pi over 4, and we know that theta is arctan of 5, and we know that phi is arctan of 2/3, so we got that. That's a neat question. I enjoyed that one. Okay, so where I want to conclude this video now is by discussing a few other trig identities that are not in the formula booklet. I don't want you to get the false confidence that you've seen it all. Okay, there's plenty of other trig formulas out there. Some are very complicated. Some are actually pretty simple. So I want to start off with those. We talked earlier about the double angle formulas, but when I was in high school, I actually had to memorize the half angle formulas as well, and perhaps you saw these in a pre-calculus course before coming to IB. If not, let's just see how to derive these, because sometimes you need to know what sine or cosine or tangent of half theta is equal to. And the easiest way to derive them is from right here, okay? And notice, of course, that theta is half of 2 theta. Okay, so what I'm going to do is, let's pretend this said cosine of alpha is equal to 1 minus 2 times sine squared of alpha over 2, right? That seems fair. That means that sine of alpha over 2 should be equal to, okay, we're going to have what's going to be 1 minus cosine of alpha, and then we're going to have to divide by 2, and then square root the whole thing. Okay, using a similar trick, but with the fact that this could also be written as 2 times cosine squared of alpha over 2 minus 1. That means that cosine of alpha over 2 should be equal to the cosine of alpha plus 1 all divided by 2 square root. Tangent is a little more complicated and has multiple forms, so I'm just going to drop these here for you to take a look at. There's 3 different ways that you can write out tangent of alpha over 2. Oh, and I forgot my plus minuses here. How embarrassing. Anyway, those are the half angle formulas. I think it's definitely realistic to say that, you know, the half angle for sine or cosine might be something that could pop up at some point in your life within the IB context. So it's good just to be able to derive those from the formulas that you have. And finally, we've got some wildly complicated ones. These are both from the homework sets to section E. The first, we have something called the products to sums formulas. So there's 3 of them, whether you have a cosine multiplied by a sine or 2 different cosines multiplied together or 2 different sines multiplied together. You can rewrite them as sums or differences. The proof of this is complicated. I'm not going to go through it, but it is true. And then we also have something called the factor formula, seen down below. Like I said, these are out there. There are a bunch of problems in our textbook and in other textbooks that kind of require you to know these. So don't try to do every single problem that you come across. If you get stuck someplace, it might be because of this, and we'll see some examples of that in the next video. I'll point some of those out. But don't worry. I mean, I think anything with the IB, they'd have to lead you into it, kind of as we saw earlier, you know, like using a particular substitution to show that something was true, and then likely having, you know, a part B with a hence or something, so you could still work your way through it otherwise. So don't stress out about these too much. I show you this just to let you know, as I said, that there's plenty more trig out there. But this is really the end of learning new things about trigonometry as far as our course is concerned. We've seen pretty much all of it that we need to know. There's some more applications coming next year with vectors and with complex numbers. But for now, this is it, you know. We'll see later on in this chapter in the next video. We'll start combining trig with previous topics that we've seen. So we'll do some inductions. Oh yeah, we'll do some sequences and series. We'll bring back quadratics, and then of course trigonometry will have a large role in calculus, but not with any new formulas or context really in the trig side of things. It'll all just be calculus. But that's a story for another day. Anyway, I hope you enjoyed. I expect you learned something because I don't think there's too many people out there watching this video who knew all the formulas on this screen at the very least. And I will catch you next time as we conclude Chapter 13.